Hello, thank you for tuning into our video. This is our final project YouTube video of a PWR nuclear reactor using PC-Tran analysis software to determine reactor characteristics of a simulated reactor over time. For Introduction to Nuclear Engineering ENGR 3501. Our group members consist of Connor Armstrongs, Fady Rizkala, Isis Martin, Ernest Bean, and Kadira Cameron. So this is our outline. We will have a description of simulation exercise 1 with graphs and figures. We will have a description of exercise 2 with graphs and figures, and we will have a description of exercise 3 with graphs and figures. We will also have an interpretation of the overall simulation results followed by a comprehensive conclusion. For exercise 1, we manipulated the control rod position in order to affect the thermal power of the reactor. We first set the initial condition to 100% at the middle of the cycle, and then we let the system equalize. The rod position was set to the desired values and reactor parameters were recorded for each control rod position. The table shown here shows the recorded values of the control rod position was lowered from 98 to 85 incrementally, allowing the system to come to steady state at each step. The rod position was brought back up to 95 in the same manner. Plots for rod position, core thermal power, steam generator pressure, and turbine demand versus time will be shown in the subsequent slides. The first graph shows how we altered the rod position over time. We may have made some errors here as there was not sufficient time for the system to come to steady state at the 95% rod position. As we got further into the simulation, the rod position failed to remain constant at the desired value due to outside influences.
This graph shows the core thermal power over time, and as you can see, it is similar to the previous graph, which would lead us to believe that the thermal power and rod position are proportional to each other. Upon comparison of the steam generator pressure and the control rod position, it seems that the steam generator pressure is inversely proportional to the control rod position. So whenever the control rod position goes down, the steam generator pressure goes up. This graph shows the turbine demand over time and looks similar to the first two graphs, so we conclude that the turbine demand is proportional to the core thermal power and rod position. For exercise 2, we manipulated the turbine demand in order to affect the thermal power of the reactor. We first set the initial conditions to 100% power at the middle of the cycle, and then we let the system equalize. The turbine demand was set to the desired values and the reactor parameters were recorded for each designated value. The table shown here shows the recorded values. The turbine demand was lowered from 100 to 85 incrementally, allowing the system to come to steady state at each step. The turbine demand was brought back to 100 in the same manner. Plots for rod position, core thermal power, steam generator pressure, and turbine demand versus time will be shown in the subsequent slides.
This graph shows the turbine demand over time. This shows how we altered the turbine demand and the amount of time we allowed the system to stabilize for each step. This graph shows the rod position over time is roughly proportional to the turbine demand. This graph shows the core thermal power over time is roughly proportional to the turbine demand. This graph shows the steam generator pressure over time. It would seem that the steam generator pressure goes up when the turbine demand goes down, but tends to decrease to stable value.
For exercise 3, similar to exercises 1 and 2, reactive parameters are recorded over time. But the difference here is that the parameters are recorded after the reactor is tripped. Values are recorded on 100-second intervals. We made the mistake of recording at 1100 seconds instead of 2500 seconds for the final row of the table. Regardless, we will continue our simulation results. This graph shows the fuel temperature over time. As you can see, the reactor is tripped at 150 seconds into the simulation, at which point the fuel temperature decreased rapidly until stabilizing at about 600 degrees Fahrenheit. We would expect that the fuel temperature would come to the temperature of its surroundings eventually. This graph shows the power neutron flux. Over time, the flux decreased rapidly at the trip and eventually stabilizes at about 3%.
This graph shows the steam generator pressure. Upon the reactor trip, the pressure increased rapidly until stabilizing at about 1050 psi. Our interpretation of the results are shown in this slide. We determined that the reactor characteristics are determined by several factors. The control rod position is a useful way to control the output power of the reactor. Turbine load is determined by the electricity demand on the turbine. Upon reactor trip, reactor characteristics behave exponentially. Conclusion. PC-Churn is a useful tool for analyzing the behavior of nuclear reactors of time. Understanding of reactor characteristics over time is important for interpretation of nuclear reactor behavior.